Hey everyone, welcome back for another deep dive with us. Today, we're going to be tackling something pretty massive.
Pretty massive, right?
We're talking about the universe,
This is always a fun one.
or at least how
Yeah.
physicists use puzzles to try to wrap their heads around it all.
Exactly. I think we've got the perfect source material to guide us.
Oh,
We're
yeah.
diving into the ideas of physicist Cumrun Vafa and his book, Puzzles to Unravel the Universe. We've got an article here inspired by it.
Okay, that's a cool title.
Right.
Puzzles to Unravel the Universe.
It's really evocative of this whole idea.
I like that approach a lot because, sometimes when you think about the universe and like how vast it is, it's easy to just feel kind of overwhelmed.
Right. Like, how are we ever going to make sense of all this?
But if you approach it like a puzzle, like there are these solvable mysteries out there.
It suddenly becomes a lot less daunting.
I agree. And that's kind of Vafa's big idea here.
Oh, okay.
That puzzles aren't just, fun brain teasers. They're actually how we make sense of the cosmos.
Okay. I'm already on board with this, so walk me through it.
Sure.
Like, how does that work?
So think of it this way. Each scientific discovery, it's kind of like fitting in a piece of this giant jigsaw puzzle.
Okay, I like where you're going with this.
Right. And with each piece, with each discovery,
Yeah.
we start to get a clearer picture of the bigger picture.
Okay, that's clicking for me. But I'm guessing it's not always as simple as just finding the right puzzle piece.
You're absolutely right. And actually, Vafa makes a really important distinction in his work
Oh.
between puzzles and mysteries.
Between puzzles
Oh, that's true.
Okay, so like what's the difference there? So a puzzle, by definition,
Okay.
has a solution.
Right.
It might be a complex solution.
Sure.
It might take centuries to figure
It's
out.
like a 1,000-piece puzzle that you just can't.
Exactly, but it's ultimately solvable
Okay.
with enough time and effort.
So like figuring out how gravity works, that was a tough puzzle to solve.
Sure.
But we did it.
We did.
Yeah. Eventually.
Right. But then you have mysteries.
Okay.
And mysteries are a whole other beast.
Uh-oh.
Because mysteries might not have answers that we can grasp, at least not yet.
Oh, intriguing.
It's like we might have the framework of quantum mechanics figured out. We've got the equations. We can make predictions.
Yeah.
But the why, the true nature of it all, that can remain a mystery.
So what you're saying is some of these physics puzzles might actually be mysteries in disguise.
That's a really good way to put it.
Whoa, okay. My mind is officially blown.
That's a lot to think about.
Yeah, but I guess that's what makes it so fascinating for physicists, right? To be working on these problems that are on the very edge of what we know.
Exactly. It's
Yeah.
about pushing the boundaries of knowledge. And sometimes it's the puzzles that lead to the biggest breakthroughs.
Right.
The ones that bring us face to face with these really profound mysteries.
And I'm guessing that's where string theory comes in.
You know it. String theory. Now, there's a puzzle that's been captivating physicists for decades.
String theory, it's like the ultimate physics enigma, right?
It's definitely up there. It's this incredibly ambitious idea.
Ambitious is putting it mildly, right? It's like physicists are trying to create a theory of everything.
Exactly. Like explaining all the forces and particles in the universe, but using these tiny vibrating strings. Can you imagine?
Okay, so you're saying everything we see, everything around us, it's all just strings.
Well, that's the basic idea.
Yeah.
But it does get very complex very fast. And one of the big criticisms of string theory, and it's a valid one, is that a lot of its predictions are virtually impossible to test with today's technology.
Yeah, that makes sense. It's not like we can just build a collider the size of, well, the universe to smash these strings together and see what happens, or could we?
Oh, wouldn't that be something? A universe-sized collider. But in all seriousness, that is one of the big challenges. But here's the thing.
Okay, I'm listening.
Even without being able to directly see these strings, there have been some pretty remarkable successes with string theory.
Really? I gotta admit, I'm a little surprised to hear that. Like what? Give me an example. Give me some string theory hope here.
One of the coolest examples, and it really gets to the heart of why string theory is so compelling, involves something you've probably heard of before, the electron.
Okay, electrons, like the things that make electricity work. I'm with you.
Exactly. So we all learned about electrons in school, but what string theory was able to do is provide a predicted range for what the electron's mass should be. And this isn't just any range. We're talking about a specific calculation based on these incredibly tiny units called Planck units.
Planck units. Okay, you've officially lost me. How tiny are we talking?
Imagine trying to measure the width of a human hair, but instead of using a ruler, you're using the entire Earth as your measuring stick.
Whoa, okay, so we are talking mind-bogglingly small here. All right, so string theory, using these crazy small units, made a prediction about how much an electron should weigh. And what happened? Were they right?
Right. Scientists were able to actually measure the electron's mass using experiments, and get this, it fell right within the range that string theory had predicted.
No way. That's incredible. So even though we can't like directly observe these strings, they're making predictions that actually line up with reality.
Exactly. And that's why this electron mass prediction, it caused a lot of excitement in the physics community. It suggests that even though string theory is incredibly complex, even though we're still trying to unravel all of its implications, it might just be onto something really fundamental about the nature of our universe.
Okay, that is seriously cool. But we've got to talk about another big player in all of this, black holes. Okay, black holes. Now we're talking. These things are like the ultimate cosmic enigmas, right?
They really are. Black holes push our understanding of physics to its absolute limit.
Yeah, I mean, just trying to wrap your head around the idea of something so dense with so much gravity that even light can't escape, it's mind-boggling.
It really is. And one of the most puzzling things about black holes is something called black hole entropy.
Entropy. Okay, hold on a second. Doesn't entropy have to do with like disorder? Like how my room goes from kind of messy to total chaos if I
Yeah,
don't clean it up for a week?
exactly. Entropy is basically a measure of how much randomness or disorder there is in a system.
Hmm.
And what makes black holes so weird is that even they, these super dense objects, have entropy.
Wait, seriously. So you're telling me that these massive objects that are basically like cosmic vacuum cleaners have a messy side? How does that even make sense?
Well, for a long time, physicists thought black holes were pretty simple, like just points of infinite density, no real structure to
Yeah.
speak of. But if black holes have entropy, well, it means there's got to be a lot more going on beneath the
My
surface.
mind is officially blown. So how does string theory, with those tiny vibrating strings we were talking about, how does that play into all of this?
It goes back to those microstates we mentioned earlier. Remember how we were talking about those Planck units, those incredibly small
Yeah,
measurements?
like trying to measure the width of a hair with the entire Earth.
Exactly. So string theory suggests that those vibrating strings, which are like the fundamental building blocks of everything in the universe,
Mhm.
they can exist in countless different states, even at that mind-bogglingly small scale.
Okay, so instead of a black hole being this perfectly smooth, featureless object, it's actually buzzing with activity at the smallest possible level, and that's what gives it entropy.
You got it. It's like if you had a giant, giant pile of sand and you tried to smooth it out perfectly. Even if you got it really, really flat, there would still be tiny grains of sand.
But yeah, you'd never get rid of all the grains.
Exactly. Those grains of sand, they're like the microstates of a black hole, and string theory allows us to actually picture those microstates and even calculate them.
Whoa. Okay, I think I'm starting to get it. But string theory's connection to black holes, it doesn't stop there, right? Didn't Stephen Hawking make this groundbreaking discovery about black holes not actually being totally black?
You're right, we can't talk about black holes without mentioning Hawking radiation. It's this amazing phenomenon where black holes actually emit a tiny bit of radiation over time.
So they're not just sucking everything in, they're also spitting a bit of it back out.
In a way, yes. And
Yeah.
string theory, it not only supports Hawking's calculations about this radiation, it actually takes things even further.
Oh, how so?
It allows physicists to calculate even more precise details about black hole behavior. Not just the radiation, but how these objects behave at the quantum level, how they interact with gravity, all sorts of things.
Wow, so thanks to string theory, we've gone from black holes being these kind of simple, even though mysterious objects, to these incredibly complex entities that could hold the key to understanding some of the most fundamental laws of physics.
It's a pretty amazing shift in thinking. And that's what makes studying the universe so exciting. There's always something new to discover, always another layer to uncover. It makes you wonder what other puzzles are out there waiting to be solved.
You said it. Well, we've covered some serious ground today, from using puzzles to unravel the universe, to string theory making surprisingly accurate predictions about the electron's mass, all the way to black holes and their not-so-simple nature. It's been quite a journey. But before we go, we wanted to leave you with one final thought. If you could solve any scientific mystery, what would it be? What question about the universe keeps you up at night? Let us know, and hey, maybe we'll tackle your mystery in a future deep dive. Until next time, keep those brains buzzing and stay curious.